Welcome everybody to Alvascience Webinar. Today's topic is molecular data curation. In particular, we are going to see how to perform data curation with our tool alvaMolecule. Before starting, a couple of things. You can write your questions in the chat. If we don't answer immediately in the chat, don't worry, we will answer your question at the end of the webinar. Finally, this session is recorded and it will be available on our YouTube channel in the next few days. I take this opportunity to invite you to check out our YouTube channel, which contains many videos about Alvascience software solutions. You can find the link to the channel on our site, alvascience.com. Without further ado, let's start the presentation.
Thank you, Matteo, and welcome and good morning to everybody. In this webinar, we will show you how to perform molecular data curation using alvaMolecule. alvaMolecule is a graphical tool that can be used to visualize and analyze your chemical data. I will show you just few slides introducing the topics that we will cover during this webinar, and I will show you the main functionalities of alvaMolecule using some examples. Okay, we have not so much time, but we will try to cover the most important features that can be used when dealing with data curation. alvaMolecule can be used to identify possible issues in your dataset, like the identification of erroneous representation or the identification of specific molecular features, so we can check if our molecules are correct or if our molecule includes specific functional groups, for example. Then alvaMolecule can be used to standardize your molecular dataset. This standardization process can be used to fix erroneous representations or to uniform the representation of specific functional groups. alvaMolecule provides also the possibility to identify duplicated structures that are present in your dataset, and that can also be used for exploratory data analysis, like the scaffold analysis. And finally, alvaMolecule can also be used to calculate a set of molecular descriptors and physicochemical properties that can be used to explore your dataset. Data curation is a fundamental step when dealing with chemical data, and now we will see how data curation is included in the QSAR workflow. In this slide, we can see the four main steps that are included in the QSAR process. Specifically, the QSAR workflow can be split in four main steps, that are data curation, feature generation, model building and validation, and model deployment. Data curation is the initial step and one of the most time-demanding tasks in this workflow. Data curation can be performed using alvaMolecule, that is our molecular worksheet. That is the topic of this webinar, so we will see how to curate our data using alvaMolecule. Then, once the dataset has been curated, the second step is the feature generation. Feature generation can be accomplished using AlvaDesk, that is our tool for the calculation of molecular descriptors and fingerprints. And AlvaDesk calculates almost 6,000 of molecular descriptors and a set of customizable molecular fingerprints. The full data set, including the molecules and the calculated molecular descriptors and fingerprints, can be saved as an AlvaDesk project. The AlvaDesk project is the input for the next step in the QSAR workflow, that is the model building and validation. Model building and validation can be performed using alvaModel. alvaModel can be used both to create both regression and classification models, to apply, to add to your models the applicability domain, to evaluate the predictability of your models using cross-validated scores, to evaluate the chance correlation of your models, and so on. You can find our webinar on how to use alvaModel on our YouTube channel. The final step in the QSAR workflow is the model deployment. models created using alvaModel can be deployed, exporting them as an alvaRunner project. An alvaRunner project is a single file that includes all the information about our models and can be used by alvaRunner to apply the models developed using alvaModel on a new set of molecules. As exporting your models as an alvaRunner project allows you to easily share them with other researchers. Finally, we also developed a software tool for de novo molecular design that is called alvaBuilder. alvaBuilder is a graphical tool that can be used to design new molecules having desired characteristics through an optimization process that is based on genetic algorithms. alvaBuilder will be the topic of our next webinar. So after this brief introduction, let's start and have a look at how we can curate our molecular dataset using alvaMolecule. So let's open alvaMolecule. alvaMolecule is conceived as a molecular worksheet that can be used to prepare your molecular dataset. Molecules can be added to your dataset loading one or more files. You can also drag and drop your files into directly into alvaMolecule, or you can directly paste the molecular sources to alvaMolecule in order to add the molecule to your dataset. You can also load multiple files, and you can merge them into a single dataset. During this webinar, we will use just one file, a SMILES file, specifically a SMILES file with header, that is a SMILES file including an additional row that includes the name of the columns that are included in our SMILES file. alvaMolecule import the most common molecular file formats, such as SMILES, MDL, and the TrypoSmall file. And when alvaMolecule loads your molecule, it automatically loads the additional columns included into the SMILES file, or the additional fields that are included in your SDF file. So we can see in this case that we loaded more than 1,500 molecules. In the status bar, we can also see that alvaMolecule automatically imported two additional columns, two additional variables. We can explore our dataset visually using the molecular grid view, but we can change this view since alvaMolecule provides two types of views, the molecular grid and the molecular worksheet. We can switch between these two views using the menu, or just using the shortcuts that are provided using in alvaMolecule. So let's switch to the molecular worksheet representation. We can see that we have a first column that includes our molecules. Then we have a second column including the name of the molecules. The name is collected from the source file. Then we have a third column that is the file name. And we can also see the two additional variables that are included, that are automatically imported by alvaMolecule. These two additional variables are taken from the molecular source, and one is the target variable, target var, and the second is a target class variable. So we can see that the first variable is a quantitative variable, and the second one is a qualitative variable. In this case, having just two values, class A and class B. We can start exploring our dataset, for example, looking at the distribution of our target var using the charts, so we can see the histogram of the target var. If the molecule files that we imported into alvaMolecule have more than one quantitative column, we can use them, all of them, to see the distribution of the values into our dataset. So this is the distribution of our target var into our dataset. We can also use the charts to filter our dataset. So, for example, we selected the molecules belonging to this bin. So 187 molecules have been filtered. So we can see in the status bar the number of filtered molecules out of the total number of molecules. So we can evaluate, we can perform a first evaluation of the distribution of the variables in the distribution of the molecules in our data set. Using the molecular worksheet, we can also, for example, change the values of the imported variables, such as the name, target variable, target class. For example, we can change this to molecule 1 that we want. We can also change the values for the target var or for the target class. For example, in this case, we can change the value to from class A to class B. We can also sort our data set with respect to a specific column. And we can also filter our data set using the molecules, the variables that are imported by alvaMolecule. For example, we can check how many molecules belong to class B in this case. So the molecules, our molecular data set is filtered, and we can see that 856 molecules belongs to the class B class. We can also change, for example, the name of the imported variables. In this case, for example, you can change to target regression. We can see that the name of the column is automatically changed, and when we will save our data set, the column will be saved with this name if we save as a SMILES file, or the additional field, if we will save an SDF file, will have this name. So we have seen how to import our data into alvaMolecule. So let's start with the curation process. So we will see how to check our structures. Then we will see how to standardize our structures, and how to identify and how to deal with duplicated structures, how to perform scaffold analysis, and finally, how to calculate molecular descriptors and physicochemical properties, and how to save our curated molecular data set. So let's start with the check of the structures. Before checking the structures, I typically suggest to change the aromaticity representation of our molecular data set to the aromatic form or to the QSAR form. The standard representation is the original form. So what is the original form? Is the representation that is included in your source file. It means that this representation can also have some possible issues, but I suggest to change it to the aromatic form or to the QSAR form in order to represent all the molecules in your data set with respect to the aromaticity in the same way. Since different chemoinformatic toolkits can represent aromaticity, can deal with aromaticity in different ways. And if we collect our data from different sources, we could find different aromaticity representation in our data set. So we changed to the QSAR form. Now we can check our structures. alvaMolecule provides a set of predefined markers that can be used to identify possible issues, possible erroneous molecular representation in our data set, or also to identify specific molecular features. For example, the first checker is a checker that identifies the multiple structures. That means that identifies those molecules that include in a single cell more than one structure, like, for example, salts, ionic liquids, mixtures, and so on. So this checker can be used to identify those molecules that in many workflows are removed before, for example, doing a QSAR model. So this checker do not mean a molecule that is identified by this check do not mean that the molecule is wrong, but just mean that the molecule has multiple structures. So some of the checkers can be used to identify possible erroneous representations. Some of them can be used just to identify possible specific molecular characteristics. for example, the unusual valence atoms checker, identify those atoms in our molecular data set that have an unusual valence. This check can be used to identify erroneous representation of molecules, like the covalent ionic bonds checker that identify ionic bonds that are represented as covalent bonds. We have a checker that identifies those molecules having a total charge different from 0. So the sum of the formal charges is different from 0. A checker that can be used to identify those molecules, including atoms not belonging to the most abundant isotopes. Then we have a checker for charged atoms, a checker that can be used to identify those molecules that do not include any carbon atoms, or those molecules that include atoms not belonging to the standard atom set, molecules having issues with aromaticity, or molecules including radical atoms. We can select the checker that we are interested in. In this case, we will let all the checkers selected. So let's perform the checking analysis. After the check structures have been performed, a window with the summary of the results of the checking of our structures is shown by alvaMolecule. We can see, for example, that we have 0 rejected molecules in our data set. It means that no molecules included in our data set are rejected. Molecules can be rejected if they are not well defined. So, for example, a smiles that is written in a wrong way. So we can identify those molecules in our data set and check them. We can also see that we have more than 700 molecules that raised at least one warning. We have 39 molecules including multiple structures. We have 4 molecules including atoms with unusual valences. And we have 0 molecules with covalent ionic bonds, 6 molecules having a total charge different from 0. A lot of molecules including charged atoms. We can see, for example, that we have a lot of molecules including the nitro groups. So nitro groups can be represented using charged atoms, charged nitrogen and charged oxygen atom. And we have also 18 molecules including atoms not belonging to the standard atom set. So this is just a summary. Let's have a look in detail at the result of the checker of the structure. So we can see in the status bar that we have 711 molecules that raised at least one warning. 12 columns have been added to our data set. These 12 columns are the molecular checker, plus 2 columns that are the N warnings and the rejected columns. N warnings column is a column including the number of warnings for a specific molecule, and the rejected is a column having a value equal to 0 if the molecule is not rejected, and equal to 1 if the molecule is rejected. So we can use these additional columns to explore our data set. So, for example, we can have a look at the molecule including non-standard atoms. So we can filter our data set. So we can see just the molecules including non-standard atoms. So we can see that these molecules are just 18 molecules. We can decide to evaluate these molecules, or for example, in this case, we can remove all these molecules from our data set, since we don't want to deal with this type of atoms. So we can select the whole data set, the whole molecules that are visible in this moment. So we can select all the molecules, or we can just select some of them, the molecules that we are interested in, and we can remove them. In this case, we want to select all the molecules, so we can use the shortcut Ctrl-A. All the molecules have been selected, and we can delete the selected molecules. So we can remove these molecules from our dataset since we decided that we don't want to deal with this type of molecules during our job in this case, okay? It depends on what we are doing, what we want to achieve. So we have reduced the number of molecules in our dataset. We can also evaluate the molecules having multiple structures, for example. Now we can see that we have 37 molecules with multiple structures. Also, in this case, we can decide to keep them in our dataset or to remove them from our dataset. Since we have just 37 molecules with multiple structures, we can decide to remove them, but we can also use, for example, some standardizers that are provided by alvaMolecule to deal with this type of structures. Okay, so also in this case, let's just remove these molecules. So we will select them all and we remove them from our dataset. Now we can check, for example, the molecules having unusual valencies, molecules including atoms having unusual valencies. So we can see that we have 4 molecules. We can highlight the warnings. Some warnings can be highlighting using the view highlights warnings. So we can see the atoms included in our molecules that raised the warning. So we can see, for example, that this first molecule have 2 atoms that raise the warning, these 2 nitrogen atoms. These 2 nitrogen atoms have just a total bond order equal to 2. We expect a total bond order equal to 3. So 1 hydrogen is missing from, we can suppose that 1 hydrogen is missing from these 2 nitrogen atoms. We can also see that we have 2 molecules with nitrogen atom having a total bond order equal to 5. We have a nitrogen atom connected to 3 carbon atoms and with single bonds, and to an oxygen atom with a double bond. These 2 molecules are quite similar. Then we have also a molecule with an oxygen atom with a total bond order equal to 1, and hydrogen is missing for this molecule. We can also check this molecule. We can also look at just this molecule using the single molecule mode. So we can see just this molecule, and we can see that this oxygen atom has a total bond order equal to 1, while we expect a total bond order equal to 2. So we have seen that we have 2 molecules with missing hydrogens and 2 molecules with an unusual valence specification for this nitrogen atom. We can, in this case, evaluate these molecules, trying to find them in public databases such as PubChem or Google Patents and Scholar. So let's have a look in PubChem. If we can find these molecules, we can use PubChem in order to find the full structure or in order to perform a similarity analysis, similarity searching, substructure searching, or superstructure searching. So we can, alvaMolecule found this molecule in PubChem. We can check it, and we can see that this molecule is represented using a charged nitrogen and a charged oxygen. So let's have a look also at this second molecule. If we find also this molecule, yes, we can find it, and we can see that in the same way, the nitrogen is represented as a charged ammonium. So we have seen how we can use the check of the structures in order to identify possible issues in our dataset. We have seen that we have identified some molecules having atoms not belonging to the standard atom set, and we have also found 2 molecules with unusual representation of the nitrogen atom connected to this oxygen atom. So what we can do, we can then standardize our molecules. So we can use the standardizers provided by alvaMolecule in order to try to fix this erroneous representation of our molecules. alvaMolecule provides a set of predefined standardizers that can be used to fix erroneous representation or to standardize specific molecular groups. Before starting with the standardization, I would like to show you another thing that can be used using alvaMolecule. One of the functional groups that is usually represented in different ways when it is represented using, for example, SMICE or cheminformatic formats is the nitro group. The nitro group can be represented, as we have seen in our data set, okay, in a charged way, so with the charged nitrogen and the charged oxygen. But some tools also represent this nitro group using 2 double bonds. So let's have a look if we are able to find in our dataset both representation. We can, in this case, use the filter by substructure tools provided by alvaMolecule. Just right-clicking on the column header, like for the other molecules, a pop-up menu will appear, and we can use the filter by substructure, just writing a smart pattern that we want to find in our dataset. So we have seen that we have the nitro group represented in the charged form. Let's have a look if we found also the covalent bond representation of the nitro group. So let's filter our dataset, including just these. We are filtering our molecular dataset, filtering only those molecules, including a nitro group represented with 2 double bonds. So we can see that we have 26 molecules where the nitro group is represented in this way. We can also highlight a substructure. So we can, for example, highlight the nitro group, or we can highlight whatever we want. When we type the smarts, we can directly see the representation of our groups in the window below. So we can highlight the specific functional groups in our molecular data set. So we can see that we highlighted this nitro group in our data set. So we have seen that we have both 2 different representations of the nitro group. We have some molecules with unusual valencies. So let's have a look at those molecules, these molecules. And we can then start standardizing our molecular structures. As I said before, alvaMolecule provides different types of standardization. For example, it can be used to convert unusual covalent bonds to ionic bonds, to remove exceeding hydrogens, to add missing hydrogens. In this case, we want to use these standardizers, since we have seen that we have some molecules with missing hydrogens. We can, for example, use the remove monatomic fragments or retain biggest fragments when we deal with multiple structures. But in this case, we already removed the multiple structures from our data set. And we can, alvaMolecule also provides some standardizers in order to represent specific functional groups in the same way. For example, we can standardize the nitro groups using the covalent bonds, so 2 double bonds. And but we can also represent in the charged form. We can standardize the azide groups or the diazo groups. We can remove radicals from our data set. We can neutralize atoms or molecules in our data set. In addition to the predefined standardizers, we can also use this functionality, that is the possibility to provide custom standardizers. Custom standardizers can be used to modify the molecules included into your molecular data set, just using the SMIRCS language that is quite similar to the SMICE language and to the SMARTS one. So in this case, we want to define custom standardizer in order to modify these molecules in order to represent them in the same way in which they are represented in PubChem. So we want to change a nitrogen atom that is connected with a double bond to an oxygen atom and to 3 additional atoms. into the representation having the nitrogen with the charged nitrogen and the charged oxygen. So we can see the reaction. In this case, I've not finished the reaction. When dealing with reaction, so with smears, we have to map every atom that is included in the reaction, and we want to be included both in the reactants and in the products. If there are no atoms that must be added or removed, we have to map every atom in our reaction. Okay, and now let's change the nitrogen to a charged nitrogen. Let's remove the double bond and let's charge the oxygen atom. In this case, we will convert this type, every molecule including this pattern will be converted to this pattern. One other thing that I would like to point out is that you can change the order of the molecular standardizers, since the order can affect the final result. Specifically, if you use, for example, standardizers that break bonds, so that create multiple structures in your dataset, and if you use, for example, standardizers that remove or that deal with multiple structures, you have to pay attention with the order of your standardizers. You can add more than one custom standardizer, but in this case, we can just use this free one. So let's do it. So we can see that, for example, these are our molecules that before were with unusual valencies. So we can see that 2 hydrogens have been added to the nitrogen of this molecule, reaching the usual valence. We can see that these atoms have unusual valence now. And we can also see that these two molecules have been changed using the custom standardizers that we introduced in the standardizers options. Okay, so we had a look on how to check our structures, so how to identify possible issues and how to try to fix them. So let's perform a check structure again after the standardization. So we can see that now we have just 21 molecules with that include some warnings. And those molecules are molecules with a total charge different from 0, 5 molecules, and 21 molecules including charged atoms. We can evaluate them, but in any case, we can decide if we want to keep them in our dataset or not. But we can see, for example, that charged atoms included in our dataset are, for example, ammonium and so on. So we have seen how to check and standardize our molecular structure. We can now see how to perform the duplicate analysis. So we have checked and fixed the erroneous representation. Now we can perform the duplicate analysis. Using the duplicate analysis, we can identify inside our dataset those molecules having the same molecular structure, or we can identify those molecules having the same value for a specific column. For example, we can, for example, evaluate those molecules having the same name if the name is meaningful, or, for example, we can identify those molecules having the same value, for example, for a target variable, the target recursion variable, and so on. This can be used to identify molecules that have, for example, the same value for our target variable in order to identify the possible, to evaluate and to explore our dataset in this way. Otherwise, we can identify the duplicated structures using the molecule option. In this case, alvaMolecule will identify the duplicated structures when the molecule have exactly the same structure. So with respect to aromaticity, number of hydrogens, and so on. But we can also choose to ignore some characteristics of the molecules when performing the duplicate analysis. For example, if we select the ignore stereochemistry option, we can select one or more of these options. But for example, if we select the ignore stereochemistry options, the two molecules will be identified as duplicates if they have the same structure, even if they have different stereochemical information. In the same way, if we select, for example, ignore formal charges, two molecules will be identified as duplicates, even if they have different formal charges. This can be used to identify possible issues in your dataset, so molecules that are the same, but with different representation. So let's perform the duplicate analysis. Okay, so alvaMolecule identified 45 groups of duplicates for a total of 90 duplicated molecules. So we have 45 molecules with at least one duplicate. We can navigate to, and we can check the duplicated structures. In this case, we can select, we can see the whole set of duplicated structures, so 90 molecules, but we can also evaluate group by group, okay? And we can check them group by group. But what we can do now, we have seen that we have duplicated structures, 90 duplicated structures. So we can evaluate them. We can check if there are some issues with these molecules. But we can also see, for example, that for the first molecule, we have the same structure, different names. But for example, we have different value for the target class variable. And while we have the same value for the target regression variable, these two variables are not connected, so they can be in this way. So we have a class that is different from these two, for these two molecules, and a regression value that is the same. So what we can do now, we can manually explore our data set, and for example, we can decide to remove one of these molecules. For example, we can decide to remove the second molecule, since we have just one molecule with the same structure and with the same value for the target regression, that in this case is the variable that we want to explore. So we can, for example, delete this molecule. So we have now 44 groups of duplicates for a total of 88 duplicated molecules. Okay, in this case, we don't have so many duplicates, so we can also check one by one every duplicated group, but alvaMolecule also provides a tool that helps us to manage duplicated structures. That is the Manage Duplicates tool. Using the Manage Duplicates tools, we can remove the duplicated structures. So just one structure for every duplicated group will be preserved, while the other will be removed. If we don't select any of the variables that are included in our dataset, just one molecule for every duplicated group will be preserved. But we can also select one or more of these variables. What happens if we select one or more of these variables? For example, if we select target regression, we are saying to alvaMolecule that the duplicates will be removed if and only if they have the same value for the whole group for the target regression variable. So in this case, for this couple of structures, they have the same value for the target regression. So they will be one of the structure, the second one, will be removed. If we, for example, select a variable that do not have the same, for example, I don't know, if we have some variables with different value for target var or target class, but we can see after the manage duplicate. So we can select the target regression. So we are saying to alvaMolecule, okay, remove just those structures that are duplicate, but if in the duplicate group, the value for the target regression variable is the same. So we have removed, alvaMolecule removed 40 molecules. So we have now just 4 groups with duplicates. that have different values for the target regression variable. We can see that they have similar value but different. Also in this case, they have similar value but different. And also, while in this case, they have quite different values for the target regression. In this case, what we can do, we can, for example, change the value for the variable we are interested in and remove, for example, one of the duplicated structure, or we can decide to remove all these molecules since they have different values and we suppose that these molecules are not reliable. So in this case, we can, for example, remove this molecule since they have the similar value, for example. And also this one. But in this case, since both of these have a different value, quite different, we can decide to remove, for example, both of them. So now we don't have any more duplicates, but we can, for example, explore again our data set, performing duplicate analysis, ignoring some of these specific characteristics. Once we have removed our duplicates, so we can suppose that our data set is quite ready, we can perform some exploratory data analysis on our data set, such as, for example, the scaffold analysis. Performing the scaffold analysis, we can identify, we can group our data set with respect with the scaffold. The scaffold is based on the Bemis-Murco frameworks. So Bemis and Murco defined 4 different frameworks, structural frameworks in a molecule, that are the ring systems, the linkers that connect different ring systems, and the side chains that are connected to a single ring system. And the scaffold is identified as the combination of ring systems and linkers. We can also use the highlights Bemis-Murco features in order to highlight these different features. So we can see that in this molecule we have 2 ring systems connected by a linker. So the scaffold is composed by these 2 ring systems and this linker, and we have some side chains. We can use the scaffold grid to filter our molecular dataset, also selecting more than one scaffold. So we can see that we have in this dataset more than 400 scaffolds. That is a quite huge number for a quite small dataset. The scaffolds are ordered by the number of molecules that are included for each scaffold. So the most frequent scaffold is the first one, with having 432 molecules. Then we go down, and the last one is include the molecules with the no scaffolds. In this case, we have 160 molecules with the no scaffolds. Molecules with the no scaffolds are those molecules having no ring systems. So we have seen how we can perform the scaffold analysis in order to perform this exploratory data analysis. So one of the last things that I want to show you is the possibility to calculate molecular descriptors and physicochemical properties using alvaMolecule. So we can see that alvaMolecule calculated 88 molecular descriptors and physicochemical properties. These descriptors and properties are automatically added to our dataset as additional columns. As we have seen before, we can decide, for example, to hide some columns directly using the pop-up menu that is available when right-clicking on a column header, or we can perform it in an easy way using the column selection tool. So we can see that alvaMolecule calculated 88 molecular descriptors, among them 31 constitutional indices that can be used to evaluate our data set, since it includes some the most common molecular descriptors, constitutional descriptors, such as the molecular weight, but also the graph density, number of atoms, and so on. alvaMolecule calculates 15 ring descriptors and a set of molecular properties, among them the molar refractivity, the topological polar surface area, 2 log-P models, and so on, and also a set of drug-like indices. So we can, for example, remove all the checkers from our view. So we can see that we have removed all these checkers. So we can see just the molecular weight, the density, and so on. We can also unhide the columns directly from the molecular worksheet, or using the column selection tool. The molecular descriptors and physicochemical properties that are calculated by alvaMolecule can be used to explore your dataset, for example, using the charts provided by alvaMolecule. In this case, we can see the scatter plot of our molecular dataset for 2 variables, that is the target regression variables and the molecular weight. We can use the scatter plot to explore our dataset, so we can check using the molecule int specific molecules having specific characteristics for a variable. We can also color our plot using one of the available variables, that are those imported variables and the calculated variables. But we can also use the charts to filter our molecular dataset. So in this case, we have filtered 5 molecules, these 5 molecules, and we can check them. We can modify the scatter. We can easily modify the scatter, and we can see how the molecules are distributed in our scatter plot. Finally, okay, we have seen how we can perform data curation. So we check the structures, we perform the standardization, we evaluated the presence of duplicates in our molecules, and we also perform some exploratory data analysis. So I've shown you how we can perform some exploratory data analysis, taking into account that the data curation is a time-demanding step, since it requires the human intervention. We need to check our molecules in order, for example, to define and to choose which standardizers we want to apply on our data set. There are some standardizers that can be used commonly, but some of them must be defined when we have already looked at our data set. So our data set is ready, and we can now save our dataset. We can save our dataset as a SMICE file with header, or STF file. Just one thing that I would like to show you is that if we filter our dataset, we can save just the filtered molecules. So it can be useful if we want to save just a portion of our dataset. In this case, we can decide to save only the filtered molecules or all our dataset in STF or SMICE file. But we can also save our dataset as an Excel file. So, and these files could be the starting point for our next step, that is the descriptor generation, the feature generation, if we are working inside the QSAR workflow. Anyway, we prepared our dataset is curated, and we can do further, and we can go further and perform the next step. I hope that I've shown you the most important features of alvaMolecule. I hope that I didn't miss anything, but anyway, if there are some questions, we can answer directly here. Thank you very much to everybody for your attention.
Thank you, Andrea. A couple of things regarding the export. Maybe we can point out about also the use of the Excel format.
Yeah. I suppose that I said it. We can save, yes, the molecules as an Excel file. This file can include the images or not of our molecules. So we can use the Excel file to share our dataset with other colleagues and researchers.
Okay. Regarding, for example, if a person wants to understand better checkers and standardizer or other part of the software, is there documentation?
Yes. Okay. You can find a lot of information on our website or on our YouTube channel, where we have a lot of short videos showing the main functionalities of our tools. But we can also have a look at the help provided with alvaMolecule. That is full detailed help that includes the information on how to use the graphical user interface, but it also includes the theoretical information about, for example, the checkers, how they work, how they are defined. For every checker we have information, and also for the standardizers. So we can check how they work, when they do something and when they do not. And we have also detailed help about the molecular descriptors and physicochemical properties that are calculated by alvaMolecule. So we have a detailed documentation that is provided by together with alvaMolecule.
We said before, but just now also in the documentation about the properties calculated by alvaMolecule. Also, Alvadesk calculates property. So what is the difference between the two software?
Okay, alvaMolecule is a software that is conceived for molecular data curation. It calculates a small subset of molecular descriptors that are specifically some constitutional and some ring descriptors that can be used to easily evaluate your molecular data sets. So they are descriptors that, as I said, the molecular weight, the number of atoms, the information about some ring properties, and we included also a set of physicochemical properties. While Alvadesk is a tool that can be used to calculate molecular descriptors and fingerprints. Alvadesk calculates almost 6,000 molecular descriptors, and these descriptors, the descriptors and fingerprints calculated by Alvadesk, can be used to build models. So in this case, we have a small set of significative molecular descriptors, while in Alvadesk we have a huge set of molecular descriptors that can be must be chosen when we deal with the QSAR workflow. So feature selection and so on.
Okay, we are close to the end. Maybe there is time for a final question. Is the scatter the only available chart when dealing with the properties calculated by alvaMolecule?
No, we have also as we have seen, we can, for example, check the distribution of a specific variable. For example, in this case, the molecular weight. We can see that the dataset is filtered. So we can see that the chart is filtered in the same way, but we have both chart, bar plot, and scatter plot. Bar plot can be used to evaluate the values of the descriptors for the descriptors of the import, or the values for the imported variable for the whole set. Just one thing that I forgot to say is that we can copy our molecule, okay, in different ways. So we can copy, for example, the molecule in SMILES, MDL, chemical formula, the images of the molecules, but also we can copy the source, so the SMILES that is in the original file or the SDF. This can be useful when we deal with, for example, rejected molecules, so we can check directly the source file in order to identify possible issues.
Okay, I think that's it for today. I wanted to invite everybody to get in touch with us, and remember everybody that you can get in touch with us through our site alvascience.com. Thank you, Andrea.
Thank you to everybody. Thank you, Matteo, and thank you to everybody for your attention. And I hope to see you again in our next webinar.
See you soon. Bye-bye.
Bye. Bye-bye.